Good evening, everybody. As Joanne said, my name's Tom Crotty. She said some things about me. Let me give you some of the things she didn't say that are equally important. And the first one of those is that I am not a chemist. I'm a pseudo-scientist, but my career has always been in marketing and those sorts of activities. I have a degree in agriculture, which has some relevance to my subject tonight, but it's a subject that I've not been involved with for many, many years. I started out with ICI. If those of you old enough will remember ICI, fading into the past. I started out in the fertilizer business and then went through plastics and fluorine and chlorine and all sorts of other molecules on the way through before joining INEOS. But I'll tell you a bit more about INEOS in a moment. So the important thing to know is I'm not a chemist. So if you've got questions around the detail of the technology, somebody else in the audience can answer them because they're far more qualified than me. But I will try and answer your questions later on. What I was going to do was start off by talking a bit about INEOS. Those of you who don't know us, Brian was saying earlier on, there you are, Brian, yes, here we are. Brian was saying earlier on that INEOS has been known as the biggest company you've never heard of, and that is probably still the case with a number of people in the room. So I'll tell you a bit about INEOS. A very short history lesson on biofuels, particularly how first-generation biofuels developed, and why we then moved on to a search for second-generation biofuels because of some of the, as Joanne said, food competition issues with first-generation. And then tell you about the business that we have developed as a result of that search and that we are in the process of commercializing literally as we speak. So let me start with a little bit about INEOS. We are a large petrochemical company, privately owned. We're headquartered in Switzerland. Our turnover is this is 2010, it was $40 billion. It's a bit bigger now, it's about 45. And we're vertically integrated. I'll show you a little slide in a moment that shows that vertical integration. So basically what we do is we start with oil and gas, and we make a whole host of building block chemicals that the rest of industry then uses. You won't have heard of us because we sell nothing to the general public. You can't go and buy an INEOS branded product in the shops, but pretty well every product you buy probably has one of our chemicals in it or in its process at some stage through its lifetime. And we've been an established producer of biodiesel and ethanol for a number of years, so we've got expertise in this area already. We're also a refiner. We have two very large refineries, which are joint ventured with a company called PetroChina, who are probably, I think, now the world's biggest company. They are certainly the world's biggest refining company, China's biggest refining company. And our two refineries are in Scotland and in France, and I'll show you a map in a moment that shows you that. And we also license a lot of technology around the world. So we don't just use it ourselves, we license it out to other people. We've a relatively young company in the scheme of the chemical industry. When you look at the likes of DuPont and Dow, who've been around forever, in that we only started in 1998, and we grew very rapidly through the noughties. With two big growth spurts. We grew mainly through acquisition. We've specialized in buying fairly unpopular businesses from large blue chip chemical companies. So a big growth spurt in 2001, which is when I came into the company, when we bought a slug of businesses from what was then ICI, and a big spurt in 2006 when we bought all of BP's chemicals business from them. So those have been the major drivers of growth. So you can see we came from 200 million turnover in 1998. By 2008, that was almost $50 billion of turnover. So very, very rapid growth. And we've always tried to do things as simply as possible, to keep it uncomplicated. So here's something complicated. This is just a quick map of the sort of product areas we're in. I'm not going to go through it in any great detail. See if I can make this work. Yes. So basically, as I said, we start with oil and gas. The oil flows through one of our two refineries into intermediate products like naphtha. We obviously make fuels. We make a lot of diesel and jet fuel. And we flow the naphtha through into our steam crackers. And we use gas as well. We're unusual in that we have 7 Crackers are the big machines in the petrochemical industry, where you're taking that basic raw material and you're cracking it into useful products. We're unusual in that of our 7 crackers, 3 of those 7 are actually gas crackers. Most in the world, most crackers are liquids crackers. They use this stream through from oil and naphtha. We have sort of half and half liquids and gas, which is very helpful these days because gas is much more competitive than oil. And once we've got to our building blocks like ethylene and propylene and benzene, we then take them through into what we would call these intermediate chemicals or finished polymers. So we make a lot of polyethylene up here, low density, linear low density and high density polyethylene. We make polypropylene. So those are the major bulk plastics that you come across every day. And then a lot of these other building block materials here go into other very critical materials. So something like acrylonitrile will go through into carbon fiber. Something like, styrenes going into polystyrene, obviously. And other plastics, most of this stuff is usually made of what we call ABS, which is acrylonitrile butadiene styrene, and we make all 3 of those molecules that go into making the plastic that makes up most of your computers, etc. So that's why you don't see us. We're in this intermediate step. Geographically, that's our spread. Mainly Europe and North America. Very little in Asia, although we have some significant growth plans in China as we speak. We're building 1 large joint venture plant in China with Sinopec, and we've got plans for 2 or 3 more. But our big sites, our 4 very big sites, are the Grangemouth complex up in Scotland. Something's gone wrong with the slide, so it's not in the middle of the sea. It is actually there. So Grangemouth produces about 12 million tonnes of products. Our other refinery down here at Levera, 11 million tonnes of refined products and petrochemicals. Cologne, huge integrated petrochemical site in the middle of Europe, and in the South Houston area, another very efficient integrated petrochemical site in the Gulf of Mexico. So that's our spread. In the UK, apart from Grangemouth, our second major site is our Runcorn site, which actually isn't in Holland, it's there. And there we make chlorine and PVC. Licenses, however, we spread all across the world. Most of our licensing work is happening in developing countries, so a lot in South America, some in Africa, a lot in the Middle East and India, and also a huge amount in China. And we're licensing a whole range of technologies, chlorine, PVC, polystyrene, polypropylene, etc. And these are the sorts of companies that we're dealing with that currently run INEOS technologies. So right through from the big names like Dow, through to the emerging names like Braskem in Brazil, SR in India, PetroChina and Sinopec in China. Let me talk about biofuels. And I'll start with, as I said, a short history. I will keep it short because, of course, biofuels themselves are definitely not new. The oldest known form of fuel is wood. Wood is a biofuel. Definition of a biofuel is it's derived from a plant material. And since earliest time, wood provided the key fuel for energy. And we began to see about, apparently, I checked this on Wikipedia, so it must be true, 3,000 to 5,000 years ago, evidence in China of coal being used. So the coal industry is actually quite an old industry, not quite as old as wood, but pretty old. And of course, when you look at coal, what you're looking at there, and this is plant material, but plant material of a very, very great age that has been compressed into a very intense form. And we really saw a growth in that fossil fuel use in the 18th and 19th century. The industrialization push really drove up usage of coal in particular. And then in the later 19th century, we start to see the growth of oil. So we start to see oil coming in. The first refinery in the world was built in Azerbaijan in 1861. And that really marked the start of the world's real dependence on fossil fuel. And if you look at that growth, it is pretty dramatic. Here's 1860, 1861. and there was a sort of slow, steady start. But then from really the start of the 20th century, that demand and growth of use of fossil fuels was dramatic. And oil really growing as a portion of that dramatically from really the early part of the last century, the early part of the 20th century. This is in gigatons of carbon per year, so the three fractions here are comparable. So we've become very dependent on fossil fuels, is what I'm basically saying. And what brought about an initial interest in biofuels? Well, in the 1970s, we saw the first oil price shock kicking in, and we started to see initial concerns starting to grow on climate change. And the first theories being postulated about the causes of climate change, driven by the very high levels of CO2 emissions that come from burning fossil fuel. And that's when initial bioethanol production started in the late 70s. By 1997, we had a global agreement on what was going on in the CO2 emissions issue. And we had the Kyoto Protocol adopted on the 11th of December 97. And that took quite a long time to come into force, nearly 10 years. Kyoto Protocol came into force in 2005. And of course, in the 2000s as well, the other driver here was a very rapid rise in fossil fuel prices. We forget that it's not that long ago that barrels of oil were priced in single dollars. You know, a barrel of oil was $5, $6, $7. A barrel of oil today is $100. And we've got very used to it, even though it's only actually been in the last 3 or 4 years that's been at that price. But now, you know, I remember even 3 or 4 years ago, we would have a big debate every year when we did our budgets about what oil price we would assume. And now that debate doesn't seem to exist because we all assume it's going to be $100. So we've got used to very expensive fossil fuel. And this is a graph that shows that growth of biofuels, the majority of which is ethanol. So this is yellow, the ethanol, on the blue fraction here is a bit of biodiesel kicking in. But yeah, slow start in the 70s, but then through the 80s, and then a huge leap in the noughties from about the year 2000 onwards. And that, as I said, is driven by the fact that we did have the Kyoto Protocol signed here in 97, and therefore government started to mandate increasing use of biofuels, but also that very high, rapid rise in the price of oil, and therefore oil-based products, actually making bio-based products more attractive in terms of their economics. What about our history in biofuels? Well, we got into this back in 2004. If I just flip back, 2004, you can see there the start of this blue piece, which is biodiesel starting to grow. That's when we came in. Why did we come in then? Because the French government were probably at the forefront in pushing for biofuel inclusions in fuel streams, and mandated a 10% inclusion in the diesel stream of bio-based diesel. And to do that, there was a big price incentive for people like us to make and build and run biodiesel plants. So we built a biodiesel facility in a place called Ballycourt in northern France, a very rural agricultural area where there was a lot of oilseed rape grown, 200,000 tons of biodiesel a year initial capacity. And in 2008, because of increasing demand, we ramped that up. We doubled it to 400,000 tons. We lost a zero there, but 400,000 tons of biodiesel. And interestingly, almost from the day we sort of put the last bolt into that expansion, things started to sort of worsen for first generation biofuels in about 2008 because of significant growing concern about the future of these first generation biofuels. And I'll explain what I mean a bit more in a second about first generation. And actually in 2008, we were, just prior to that period, we were debating where were we going to build our next biodiesel plant. And we were debating building one in Scotland to feed into our refinery in Grangemouth. But then the mood changed significantly. So what are first generation biofuels? Well, they're made from sugar, starch or vegetable oil, basically. So you've got the ethanols, the alcohols made from sugar or starch, and you've got biodiesels made from fats of some sort or another. So the alcohols Bioethanol from sugarcane. Brazil is the biggest single producer of bioethanol in the world. Bioethanol from cornstarch in the United States. So between them, Brazil and the US represent most of the bioethanol produced around the world. And then a bit now being produced in the UK from wheat. There's a plant in the northeast producing bioethanol from wheat starch. So it's a relatively simple process in that the carbon that you're trying to get to is fairly accessible because it is in the form of sugars or in the form of starch. So it's, basically what you're doing is replicating the digestive system that we use ourselves to access the energy from those food crops. But in this case, we're capturing that energy as bioethanol. The alternative is the system that we were using, which is biodiesel from fats by a process called trans-esterification. And the major sources there were from rapeseed oil, what we've been doing in France. But other vegetable oil sources have been used: soya, jatropha, mustard, flax, sunflower, palm oil, etc. And there is a bit of biodiesel production from animal fats as well, but the economics of that aren't brilliant. What's the problem here? Well, the problem is basically the sustainability of those feedstocks. You've got a lot of competition for land with food crops. There's food use competition for those feedstocks. So if you have a ton of wheat, you can clearly make bread from it. You can feed it to cattle and make meat from it, or you can make it into fuel. And the risk here that I think people are starting to see is the potential to drive up food prices at a time when the world, particularly post-2008, was slipping rapidly into recession. The last thing governments around the world want to see is food prices going up in the teeth of a recession. And the other issue here is that in terms of the greenhouse gas emissions from a lot of first-generation biofuels, you can actually, if you're not doing it well, you can approach the same level of emissions as you'd be getting from using oil. If you do it well, you can do it for about 70% less emissions. But once you start moving products around, you're burning fossil fuels to move the products. You're burning fossil fuels to process those products. And you can end up with some first-generation biofuels producing exactly the same amount of CO2 as the oil that they're fundamentally replacing. So what are second-generation biofuels? Well, they're again manufactured from biological source, from plant material. They're manufactured from various biomass sources, and they tend to be made from what are called lignocellulosic biomasses, basically tougher stuff. If you imagine the difference, if you imagine a wheat, an ear of wheat in the field, you've got the actual wheat in the ear, which is easy to access. The starch is easy to access. You grind it into a flour, you can access it very quickly. There's also plenty of carbon and therefore energy captured in the straw, but it's very difficult to access. It's tough and hard to get at. Likewise, wood, the same thing, it's harder to get at. But what you've got with these sorts of feedstocks, woody crops, agricultural residues and wastes, and even domestic waste, because we're actually using domestic waste in our process as well, anything that has a source of carbon, lignocellulosic carbon you can get at, you can access it this way. There is not a food competition issue. That's the key thing. You're getting away from that food competition issue. The same issues apply, though, on CO2 emissions. If you do it badly with second generation, you've gained nothing. If you're shipping agricultural waste halfway across the country to use it, you haven't really achieved very much. So that's another key aspect here. So what we've seen is what we call here an emerging bioeconomy in the last few years, with the societal needs being a need to combat climate change, a need to efficiently use waste, a need to diversify our energy base, and hopefully in the process have an economy that's producing some jobs and some wealth as well. Governments using mandated targets for things like renewable energy, proportion of energy coming from renewable sources, wanting to reduce their own country's carbon emissions. On the waste side, getting away from landfill, diverting products away from landfill, and obviously making sure in all of this you're maximising recycling and recovery of materials. And so what we did was we came up with a business which we call INEOS Bio, to develop a cost-competitive, low-carbon biofuel for existing vehicles. So you don't have to change your car in order to use it. Something that preferably allowed us to get some energy out of it, distributed energy, that was robust, reliable, and safe, and could be commercialized. So that was what we set ourselves as a target. In looking at what to produce, should we do biodiesel, which we knew and loved, or should we do bioethanol? This answered our question. This is taking a graph I showed you earlier and updating it up to 2010. The green is basically bioethanol. This is biodiesel. So you've got Brazilian ethanol, US ethanol, European or other ethanol, and then these biodiesel fractions. So basically, in producing a global business, it's the ethanol that was of more interest to us than the biodiesel. So what's INEOS Bio? Well, basically, this is a technology that was developed back in 1989 in the United States, and which we bought. It uses in 1989 they discovered a bacterium called C. Ljungdahlii, which consumes carbon in the form of carbon monoxide and excretes ethanol. Basically, that's the heart of the process. And in 2003, we developed a demonstration unit, or we had a demonstration unit that proved it works, that showed we could take whatever the carbon feedstock was, convert it into a gas that you could feed these bugs on, and then take the ethanol away and distill it and purify it. And in 2008, we created the business. And in 2012, we have built the world's first commercial plant. And I'll show you some pictures at the end to prove that we have actually built the plant. This is a schematic of the process. I won't go into it in any great detail, but basically what you have here is a feedstock arrives. The key thing with the feedstock, as I said, is that it mustn't arrive from too far away. Because if you haul bulky waste material too far and burn a lot of fossil fuels doing it, then you've not really achieved very much. And that basically determines the scale of this whole operation. So the concept here is you build a very small biorefinery. You don't build a mega refinery like the ones that we ourselves run, producing 200,000 barrels of fuel a day. You build small, localized refineries that take the waste material from a very small local area. So we take the feedstock in, we dry it, and then we gasify it, and we produce what's called a syngas, which is more or less basically carbon monoxide, which we can then feed into the fermenter where the bacteria live. And we take care of the bacteria with great care. There's various nutrients pumped in here. We keep this very, very constant. You mustn't allow the conditions to change very much in here. Otherwise, you end up killing the bacteria and killing the process. This whole process gives off waste heat. So the bacteria generates a lot of waste heat. We have some waste heat coming off this syngas here. And that allows us to generate power. We take that as steam. We convert the steam into electricity. That electricity is reused in this whole process to run it, and half of it is available for export onto the grid. So this process not only produces fuel, it produces spare electricity as well. Once we've produced the ethanol, it goes through a filtration, a distillation system, and a purification system, and then we have something you can actually put into your car, either directly or as a blend. So that's the process. There are various other ways to get to bioethanol. We've already talked about this top one. This is the first generation route. You take sugar and starch crops, hydrolyze them, ferment them, get to bioethanol. You can use cellulosic material through this route. This is what we do. This is the lignocellulosic and other biomaterial, pre-treatment, gasification, fermentation, and into bioethanol. And the key enabling technologies are these two here. It's the gasification and the fermentation that's the heart of the process, is the magic behind this stuff. So it's a very efficient synthesis of syngas to ethanol. There's the chemistry for those of you who are interested in it. I'm not going to ask questions later. So we use fermentation, said, using a naturally occurring bacterium. It's very high yield, it's selective, it's efficient. It uses relatively low temperatures and pressures, which is important because it means that it's not a hugely expensive process to build. It's tolerant to syngas composition variants. So the key thing here is that you want to have something that you can throw pretty much any waste carbon at, and it's still going to work. You don't want to be very selective about your feedstock. You don't want to be turning feedstock away and saying, sorry, we can't use that because it's not the right quantity, it's not the right quality, it's not the right moisture content. We use pretty much anything here. And it's the gasification step that allows us to manage that process. And it's got some significant competitive advantage. If you look at the relative energy cost, where crude oil is here as 1, gasoline is here, about 1.5, corn ethanol, similar, so it's quite expensive. The feedstocks that we're using here, this is municipal solid waste, wood waste, or agricultural residues, relatively very, very low cost of energy. And in terms of the life cycle assessment, this is looking at it through a sort of waste management lens. For various waste, green waste, mixed waste, waste wood, food and garden waste, the alternative technologies, this is the climate change impact. This is tons of CO2 per ton of waste, basically. So if you take green waste, so let's say your lawn clippings, your lawn cuttings, windrowing would be the traditional way to deal with that sort of waste. You basically leave it to rot and let the weather sort it out. That's pretty neutral in climate change. It should be neutral if you think about it, because what you have is a plant that grows, it grabs all the CO2, it fixes CO2, and then you allow all that CO2 to go back into the atmosphere by letting it decay. So it should be CO2 neutral. We're actually better than that, making more efficient use of that CO2. If you look at mixed waste, so this is, say, municipal solid waste, landfilling has a very, very poor CO2 impact, or a very high CO2 impact. Incineration and using that to create power through a combined heat and power plant is actually much more efficient. But again, our process is yet more efficient in terms of CO2. Waste wood, combustion, or our process, not much difference. And food and green waste, this is anaerobic digestion, which is what a lot of food and green waste is put into now. And the government are quite active around encouraging anaerobic digestion. We're actually more efficient than anaerobic digestion in terms of CO2. But the key thing there is AD is probably better if you've got very wet waste. It's very, a slurry. You would not put a slurry into our process because we'd have to spend so much energy drying it down that you wouldn't use it. So anaerobic digestion has its place there. So taking us to our first INEOS Bio plant, which we built in Vero Beach in Florida. Why in Florida? We actually started off with 2 parallel projects, one to build in the UK and one to build in the US. And the US government were hugely supportive of this technology. And they gave us a significant grant and loan guarantees, which allowed us to get on with this straight away. So that's why we built it in Florida, purely and simply that. This is an 8 million gallon per year bioethanol facility, which produces about 6 megawatts of power in addition to the fuel. It uses vegetative and yard waste, as they would say in America, and some municipal solid waste. We awarded the contract to AMEC to build it in November 2010. We broke ground in February 2011, and we've been commissioning it for the last 2 or 3 months at the end of 2012. This is the layout of the plant. This is an actual aerial photograph. So here's where the waste comes in. Gets cleaned up, tidied, and sent into the gasification plant where it's converted into the syngas. The syngas then flows through into the heart of the process here, which is the fermentation column. The fuel from the fermentation column then goes through to a distillation and storage. From there it can go into the network. The spare power coming off the gasification and the fermentation goes into a small electricity generating unit here, small power generation plant. That's basically it, and there's another view of it showing it from a slightly different angle, just as I said, to prove that it does exist. And it is in Florida. This is the waste that we get. You can see it is sort of relatively dry, bulky, fibrous, semi-woody type material. But it can take pretty much anything. We have plans to build our second plant in the northeast of England, in Middlesbrough, on one of our sites. And that plant would be built around municipal solid waste. So basically, the waste that would otherwise go to landfill could come to us. It's got a high carbon content, so things like plastics that are in there, we're fine. We can gasify them into a syngas because it's the carbon that we're after here. So we've got that as our second plant in mind. We're still trying to raise the financing to do that. And just to finish, clearly this is a large unit. It has hazard associated with it. We're very key on safety, but there are some biological hazards in Florida that it's hard to predict, and you have to manage, and there's one of them there. That's it. So any questions, I'd be more than happy to take them. One benefit we have, of course, is we are already producers of fuels, so we have an established customer base. The development of the market, so I mean, basically our customers are large fuel retailers. How it develops really depends on a lot of government issues. That's key here. In the UK, for example, we had originally mandated a 5% inclusion of biofuels in the fuel stream by 2010, rising to 10% by 2020. And then the scares around first-generation biofuels kicked in. So everyone said, "Whoa, stop! If we push for that 10% inclusion, we're going to end up ploughing up fields that otherwise we'd be using to produce food and planting biofuels, and that's not a clever idea." So those targets have been pulled back quite sharply. And the way they've been pulled back is basically by the government not supporting biofuels as strongly by incentive than they otherwise would have. So it's a hugely political issue. Our view is that we're obviously sufficiently confident to make, these investments are not insignificant. Obviously sufficiently confident that there will be a large future market, and that graph you saw will continue to rise. And that what we're doing here represents a better option than first generation biofuels. So even if what we do is substitute first for second generation, we're doing okay, even if there isn't overall growth. We think there will be overall growth. Yes, it's the short answer to the last part. Our intention is not to build lots of these ourselves. Our plan is to build a few to get the ball rolling. We've got the one in Florida. We're looking to build another one in the UK. We might build another one out in Asia. And that's really to show people that the technology works. This only works if it's localized. The footprint, it depends on what you're used to looking at. Obviously, if you're used to looking at refineries, it's tiny. The scale of that plant is smaller than the optimal. The optimal would be about double the size of that plant that you see there. The footprint actually wouldn't be much bigger, but various of the vessels would be bigger. If you look at what I'd call there are two ways of looking at this. There's an urban environment and there's a rural environment. The rural environment, I think, would tend to be smaller plants like that one, because you'd be pulling agricultural waste from a reasonably small radius to avoid burning a lot of CO2 and moving stuff around. In an urban environment, the maths would basically be that if you've got a conurbation of about 1 million people, they produce about 800,000 tons of municipal waste. That would be sufficient for a plant about twice the size of the one you see here, which would give you enough bioethanol for a 10% inclusion in the fuel consumption of 1 million people. So that's the sort of optimal urban scale that we'd be looking at. So you imagine a city like, well, the sort of conurbation around Teesside or Liverpool or Manchester, you know, that would be the optimal way. And you can replicate that all over the world. And we've had a huge amount of interest from China, from India, even, can you believe it, from the Middle East, where you think they're swimming in oil. But a lot of, you know, there's a huge pressure in the Middle East as well to find carbon neutral solutions. So yes, our plan would be to franchise this technology, or not to franchise, to actually to license it. We have an ash from the gasification. It amounts to about 7% of the initial volume. It's a very clean ash, and at the moment we are working with the building industry, and we believe that they will take the ash for plasterboard, for floor screeds, etc. And so that's the way that's developing. The biggest issue that we have in terms of the closed loop is the one you've just mentioned, which is the waste from the gasifier, which is an ash waste. Pretty much everything else is pretty well contained. But there must be some nitrogen, I agree. We haven't built that assumption in. We're using good old-fashioned distillation techniques.
Because you've got the energy.
Yeah, we have got the spare energy to use. I mean, and even with running those columns, or running that column, we still have half of the energy left for export. So yeah, it is a very sort of strongly exothermic process. Well, there must be. As I said, the microbe that's being used has been used from lab scale since 1989. And in a sort of commercial scale for, well, nigh on 10 years now, 9 years, and it works. So at the moment, it's leave well alone. No, we actually do end up taking water out at the back end of the process as well. Yeah. I mean, it depends on what the requirements are locally, but you do need to get to a set water content, so we do adjust it, and that's another use of the energy that we've got is to take the water out. If you look at compared with the best of the first generation. This is probably about 30% better than the best of the first generation, but massively better than the worst of the first generation. It does vary, obviously, depending on the individual circumstance that you've got, what your waste stream is, how far it's got to move, etc., etc. But that does actually vary. But as we sit here today, this looks about the best that there is. We've not seen anything else that gets down to this level of carbon intensity so far. The cost of a barrel? I don't know. I'll be honest, I don't know. It relies on fuel incentives. We couldn't make money on this purely on a commercial basis. So it still relies on having those fuel incentives. Once you get the technology, and that's because the capital cost is high, because these are the first plants of their kind that are being built. So what you see there in Florida is $120 million, just over $120 million. And it's producing, what I say, 8 million gallons. So you can work that out. That's not going to give you much of a return very, very quickly. That 120 million will come down rapidly as you replicate the technology, obviously. And therefore, it will become much more commercially viable. But it won't, certainly in the initial phases, it requires some subsidy to make it work, as do all the biofuels. I think with this technology, you're limited by the availability of waste carbon. The whole driver here is we want to use a waste stream, because if you use a waste stream, the CO2 benefit is much higher, because that waste is otherwise going to go into a process that's going to generate a lot more CO2, particularly if it's going into landfill. Clearly, we could put we could run this as a first-generation process, and we could grow crops to feed into this as well, but that rather defeats the object. So I think we're limited by that.
My point was slightly different.
Yeah, right.
I'm not sure how quickly we're burning bottled sunshine, but it's several, but it's measurable in centuries per year.
Yeah.
Now, if that's right, then you couldn't do as much as 1%. I just wonder if that's right, or if there's something I'm missing.
No, I think that's probably right. Well, just coming on to the first bit, which is around the plastics. Clearly, plastics would represent another viable feedstock. The issue there, I spent a lot of time, I'm a Vice President of Plastics Europe, so I spent a lot of time worrying about plastics and life cycle analysis on plastics. And there is a very clear waste hierarchy that we're trying to push and to follow in plastics, which is that, the first thing you do is reduce the amount of plastics being used, then you actually make sure that you reuse them, and then you recycle them, and then once you've got to a point where they have reached the end of their useful life, that you recover the energy from them in some way, shape or form. And clearly, you saw one form is to incinerate them and make power. This is another way of using them. But clearly, the more successful we are in managing reuse, recovery, and recycling, the less plastic you need to recover the energy from. So I think that's what's going to limit the total amount of plastic that's available to you. We actually, it's one of these quandaries in a way for us, because on the one hand, it'd be great for a technologist to say, yeah, bring it on, we'll have all the plastic you can throw at us, but actually that's the wrong thing to do. As a plastics producer, we don't want to see that happening. We actually want plastics to be used responsibly, and that would be irresponsible. Absolutely, yeah. So from that point of view, I would say they are first generation, because you've got land competition. Now, he clearly would argue, so, well, there's not land competition because nobody wants the bloody food if I produce it. But from a sustainability point of view, it is using land that could otherwise be growing food. It's a tough one. It's pretty clear to me that in the great scheme of things, we should be using the land to grow as much food as we can. That has to be the right way forward. And that if you find alternative ways of producing the fuel, then that's a much better approach. We haven't, but there are a lot of people, obviously, who are looking at it. I'll be honest, one of the problems for me with it is that carbon capture and storage is a very expensive process. It's a big risk financially, and until various governments around the world make their minds up about what they want, it's quite a risky thing to be involved in. If you talk to BP, they'll give you their bitter experience on carbon capture and storage, where they'd done a lot of work prior to the government's CCS competition that they had a few years ago. And then the rules got changed at the last minute, and they were not happy. So we've not got into the CCS side of it at all at this stage. It may, Brian. I think there's a lot of technologies that are in the hands of the chemical industry that have yet to be developed and exploited for energy, full stop. And the one you've just described is one. There's the whole concept of synthetic photosynthesis is clearly a way of cutting out the middleman here. Let's just get the energy straight from the sun through a chemical photosynthesis, which is what the plants are doing for you. So there is the start of quite a lot of interesting work going on around Europe, particularly at the moment, on those sorts of technologies. But you're talking about a long time to develop that and scale it up. And I would agree with him. I mean, I think there is, and I think the issue for me is the fact we have got 250 years worth of gas should be something we can celebrate and find a way to make it 1,000 years or 2,000 years of gas. Because if you look at renewable technologies generally, they are intermittent. Wind, solar, etc. They're intermittent. They require a backup generation process. Otherwise, we switch the lights off in the winter. So you have to have a backup generation. And for me, gas is the obvious backup generation. It's a much lower emission technology than coal or oil burning. So let's stretch it out for as long as possible. And yeah, great if there's 250 years worth. And, there's a whole range of technologies. Clearly, fracking has created the ability to get out a lot more gas than we thought we could. There's a lot of coal still there that if you manage through sort of coal bed methane systems to extract the energy from them, that could give us another source. But for me, I don't think it's incompatible to have that and what we're talking about here, or any other renewable technology, to be honest. Yeah, well, absolutely. And the municipal waste only works if it's part of a proper waste treatment system. So clearly, good quality municipal waste management now works through a process whereby you recycle everything you possibly can, you extract the metals, you extract as much of the viable plastics as you can, all of those things, leaving you with a fraction that is not recyclable. And that fraction tends to be fairly high carbon, fairly dry. So it's things like, quite a few of the plastics that don't get recycled, a lot of films. That is then shredded and or pelleted in some form. And today that tends to, if you've got a good system, that would then go into an incineration plant. The alternative is we would use it. But what we can do with this process is we have a very good capability to handle huge variations in what's in that waste. Obviously, what we would not do is throw into our gasifier black bags of waste that have got everything in there, including lumps of metal and everything else. You have to have that pre-treatment system. But every decent municipal waste management system now has that, or is getting to that point. We have a water content level beyond which we won't go, because then the energy balance doesn't work. So if it is extremely wet, I think take it, if you can pour it, we won't use it. But pretty much if you can't pour it, we'll use it. We will dry it down significantly. No, the nutrient flow is very, very low, and is just to basically maintain the conditions in the fermenter. But it's a very, very small input indeed. Yeah, bear in mind that this is not consuming additional energy. It's more than self-sufficient in energy terms. But the difference is basically if we take it through to a fuel, it's displacing a fossil fuel burn, and therefore you can credit that carbon back to this process. So it is more CO2 efficient than if we simply burned it to produce electricity, because of the displacement of the fossil fuel. It depends entirely on the food balances, doesn't it? I think, if you've got the point where you have more land than you require to grow the food you need, then you can use that land, and you haven't got a food competition issue. Well, I think one of the drivers for what we're doing here is, I think, in a lot of developing countries, this technology represents an opportunity to help to confront those problems. We saw a lot of concerns about the amount of palm oil growing that was going on in developing countries, that was creating direct food competition in countries that had a serious food deficit. So, that's an issue we're trying to address with this. The US is a different situation. The US government has decided that it wants to back this technology and has done it massively. But it does come down to the balance, the food balance.